So let's try to really understand what K equilibrium means. When I say K, I mean K equilibrium, which is the ratio of products over reactants. K equilibrium, I also mean Kc, I also mean Kp. Those are all the same ratios. Okay, so here, look at this reaction here. Let's say that reactants are going to products. When the reaction's all done and you have reached equilibrium, let's say you have one of these and you made 1,000 molecules of the products. The ratio is going to be really big. The ratio is equal to products over reactants, which is equal to be 1,000 over 1. So what that means is that your K will be really big, it's 1,000. So what that means is that you made a lot of products. If you were trying to make money making the products, you'd be very rich. Here are the reactants. When the reaction's all done, there's not going to be much left over that's left unreacted. Okay? So if the K equilibrium is really, really big, a lot greater than 1, it's product favored. You're going to make a lot of products. The product predominates at equilibrium. If you do the reaction and you look into the beaker and you have 1,000 of these left over and only one product, and you wait 1,000,000 years and it's not proceeding, that means you have reached equilibrium, because that's 1,000, it's no longer changing. And so if you see the ratio, it's going to be products over reactants, 1 out of 1,000. What that means is this: you made one molecule and you have 1,000 molecules of the reactants that's left unreacted, and your reaction is done. Okay, therefore your ratio 1 to 1,000 is going to be really, really small, 0.001. So if you have a really small K equilibrium, that means it's reactant favored. At equilibrium, you're going to have a lot more reactants than products. Okay. Now there are some ways to manipulate the equilibrium constants. Okay, one of them is flipping or reversing the reaction. Okay, so let's look at this. So here you have N2O4 becoming NO2. Kc would be products, NO2, squared, divided by reactants, N2O4. And Kc is tabulated to be 0.212 at 100 degrees Celsius. Okay. Now, what if I reverse the reaction? If I reverse the reaction, this will go to I'll flip this here. So I'm going to write this first, 2NO2, arrow, and the reactants becomes the products, N2O4. Okay, so now my new Kc is equal to N2O4 to the first power and NO2 to the second. Okay, so obviously if you flip the reaction, these two flips. So now this will also flip, so it's now going to be in the denominator. 0.212, 0.212 over 1. So in essence, you just took the inverse of this number. So take the inverse of that number, 1 divided by 0.212 equals 4.7. 4.72, unitless. So you just increased your Kc by flipping the reaction. Okay, so here's an example problem. Please pause the video and try to do it yourself. Okay, so you have the equilibrium constant for the reaction N2O2 to form NO equals Kc equals that. Oh, so it's right here. So it looks like it got cut off. Oh no, yeah. Okay. Using the information above, write the equilibrium constant expression and calculate the equilibrium constant for the following. So if you compare those, it looks like it got reversed. So the new Kc is equal to products, so N2 times O2 divided by NO squared. Okay, the new Kc is going to be equal to, since you reversed it, it's going to take the inverse of that, 1 over 1e negative 30, which is 1 times 10 to the positive 30. And that's what happens when you take when you reverse the reaction. You take the inverse of the Kc. Okay, that's one. What if you multiply the whole equation? Let's see what happens to Kc. So here's N2O4, here's NO2, second, here's the K equilibrium, products to the power of 2 over reactants to the power of 1, and it's 0.212. What if I double it? This used to be 1, now I doubled the reaction. I multiplied it. Okay, and I'm taking the 2 and I'm doubling it. So your new Kc would be NO2 to the power of 4 now, divided by N2O4 to the power of 2. Okay, so as you can see, this got doubled and this got doubled, so it's the same as taking whatever you multiplied and putting it as exponent. So if you double the reaction, you take it to the power. You let's see, you raise it to a power that is equal to that number. If you double it, you go to the power of 2. Okay, so if you double the reaction, that means you square the Kc. Okay, so 2.212 squared is equal to 0.0449 is your new Kc, which it got worse. So don't do that. Okay, so it must be because there's too much of this going on and it's going backwards, so it's not good to double it in this case. Okay, so let's go ahead and look at Hess's law. What if now, okay, so what we've done in the past is, look, first we took the reverse, then we multiplied it by a certain factor, we double the whole reaction. For this one, we're going to add 2 equations. Let's see what happens to Kc. Okay, so you might wonder, when would I have to add the equations? You have to add the equations if a reaction happens in 2 steps and you can't get the energy or the Kc of the overall reaction. So you have to do one at a time. Okay, so first thing you have to do is to add these 2 equations. Cancel out, this is the intermediate. So you're going to have 2 NOBr plus Cl2 arrow 2NO plus 2BrCl. Okay, let's say you really want to know the Kc of this reaction, but you can't do it because it happens in these 2 steps. So the first thing you did was you got the Kc of the first step, which is equal to 0.014, and the Kc expression would be NO right here to the power of 2. Br2, you still have to write that, divided by NOBr squared, because of this 2 right there. Now the Kc for the second reaction would be BrCl, this right here, squared, over Br2 and Cl2. Okay, so you got the Kc for this one is 0.014, you got this Kc for the second reaction is 7.2. What is the Kc for the bottom one then? Okay, so do you think you should add them? Do you think you should multiply? Do you think you should subtract? Okay, so the way we know what to do with those 2 numbers is to look at these 2 reactions, see what we need to do to these 2 to end up with whatever this is. Okay, so let me go ahead and write the equilibrium expression for this. The equilibrium expression is equal to NO squared times BrCl squared divided by NOBr squared divided by Cl2. Okay, so what must I do to this and this to make it look like this? Should I add them? If I add them, I have to get the common denominator. I don't want to add them. Why don't we try multiplying them? Because if I multiply them, I can see, okay, let me just rewrite this one. I'm going to recopy this here. Okay, I'm going to recopy NO squared times Br2 divided by NOBr squared. Okay, so it looks like this and that matches, that and that matches, but it looks like something's happening. So let's try multiplying it with this and see what happens. So BrCl squared over Br2 Cl2. Okay, when we multiply them, it looks like something cancels. Br2 cancels, and I end up with, it matches. So here's the NO, here's the NO2. So NO squared. Here's the BrCl squared, BrCl squared. NOBr squared, NOBr squared, Cl2, Cl2. So to get this final equation, what did we do to the two reactions? We multiplied them. Okay, so therefore, what must we do to the two KCs? Yes, we must multiply them. Okay, so 0.014 times 7.2 equals 0.1008. So 0.014 times 7.2 equals, let me just do it. This is 0.014. This is 7.2 equals, the Kc for this one is 0.10. 0.1008, 0.10 with 2 sig figs, and that is the Kc. Okay? So here's a summary. If you reverse the reaction, what do you do to the answer? You take the inverse, right, of the K. K reverse is the inverse of the K forward. Okay, if you multiply a reaction by a number, the K is raised to that power. Kc for a net reaction, if you have to add the steps, you have to multiply the Kc's of the individual steps. Like we did here. We multiplied this one, these two. Okay, here's a sample problem. So given the following information, you have two reactions, find the Kc for the final reaction. And here's the answer. So what I'm going to do is I'm going to manipulate this reaction to make it look like that. Okay, it looks like, so I have to consider reversing it or not reversing it. So the HF is on the left side, so I'm going to just copy it. Okay, so HF, arrow, H plus F minus. I didn't really do anything to it, so I'm just going to write the Kc, 6.8 E negative 4. Okay, now look at the second reaction. It looks like this needs to be on the product side, right? So what I'm going to do to this is I'm going to flip it. I'm going to reverse this reaction. This one I did nothing for now. So I reverse this one. So I'm going to take this H2C2O4 and I put it on the right side. And then this will go on the left side. Okay, so if I reverse it, then this I must take what? What should I do? You're right, the inverse of it. 1 over 3.8 E negative 6. Okay? Now, let's go ahead and add those together to see what I got. Okay, so I have HF on this side. Two H plus, it looks like I need double of this. Do you see that? Two F's. So to only get two F's, I'm going to have to double this whole thing. Okay. Also, you can see that the HF, I need to double it because there's 2 right there in the end. So if I double it, what should I do? Do I double this? No, I raise it to the power of 2. I square it. All right. So now let's see if this works out better. Does it look like that? Yes, I think so. You cancel the H pluses. And there's the 2HF. And it matches this. Yes. Here's a C2O4. C2O4 minus 2. Check. That checks this one out. Yes. And then I bring this down. 2F minus. Yes. It matches. And then this is this. Yes. And then I write that down. H2, C2O4, and it matches. So it adds up and it matches the final equation. Determine the value of Kc. To get the final Kc, what must I do to these two numbers? I must multiply them. Because that's what we did over here. We multiplied the numbers when we added the reactions, okay? So the final answer would be 6.8 e negative 4 squared, that's the first reaction, multiplied by 1 over 3.8 e negative 6, that's this right here, and you should get 0.12, and that's the correct answer.